This is Module 4 for Chapter 19 on the circulation. In this module, we'll look at the regulation of blood pressure and blood flow. We'll be spending our time looking at the regulation of arterial blood pressure. Let's begin with the short-term neural regulation, and this is going to involve a reflex. You may want to go back and review the components of a reflex arc that were covered in AP1. We'll begin with the baroreceptor reflex. Baroreceptors are mechano or stretch receptors, and they monitor blood pressure. The main baroreceptors are located within the carotid sinuses and the aortic arch. The stimuli for the baroreceptors is an increase in blood pressure. Remember, these are stretch receptors. Blood pushing up against the walls of the vessel is what creates your blood pressure. As the volume of blood increases, this will stretch the receptors further, acting as a stimulus. So an increase in blood pressure is what stimulates the baroreceptors to fire. The control center is located in the medulla of the brainstem. It is called the cardiovascular center. There is a cardioaxillatory nucleus as well as a cardioinhibitory nucleus. In addition, there is a vasomotor nucleus. The cardioaxillatory nucleus will increase heart rate and contractility. The inhibitory will decrease heart rate. The vasomotor center will bring about vasoconstriction or vasodilation. The effectors of the heart will include the SA and the AV nodes, as well as the myocardium of the heart and the smooth muscles in the blood vessels. In this illustration, on the left, you can see the baroreceptors in the carotid sinus. You can also see the baroreceptors in the aortic arch. We'll talk about the chemoreceptors later. Let's go over how the baroreceptor reflex works. Keep in mind that baroreceptors are stretch receptors. What will stimulate them is an increase in blood pressure. So let's begin there. When the blood pressure becomes elevated above normal, the stretch receptors will fire. So the carotid sinuses and the aortic arch receptors will fire, and these are your baroreceptors. That information will be sent by way of the afferent nerves to the cardiovascular center. Remember, blood pressure is elevated. So what we'll need to do is decrease sympathetic input to the SA and the AV nodes, as well as the myocardium, and decrease sympathetic input to the blood vessels. In addition, we're going to increase parasympathetic input to the SA and the AV nodes. If you increase parasympathetic input to the nodes and decrease sympathetic input to the nodes, the heart rate will go down. If you decrease sympathetic input to the myocardium, stroke volume will go down. In addition, decreased sympathetic input to the blood vessels will bring about vasodilation, both of the arteries and the veins. Recall that cardiac output is equal to heart rate times stroke volume, so this will decrease cardiac output. In addition, vasodilation will bring about a decrease in the total peripheral resistance. This will lead to a decrease in blood pressure, returning it back to normal. Now let's look at the opposite. When your blood pressure falls below normal, keep in mind the baroreceptors are stretch receptors, and so they will stop firing since they are not being stretched. The cardiovascular center then will increase sympathetic input to the heart, both the nodes and the myocardium, as well as to the blood vessels. At the same time, parasympathetic input to the nodes will decrease. As a result, your heart rate will go up, and in addition, your stroke volume will go up. Recall that increased sympathetic input to the myocardium is going to increase contractility, which is one of the factors that will influence stroke volume. Lastly, you're going to have vasoconstriction of your arteries and your veins. When heart rate and stroke volume go up, cardiac output increases. When you have vasoconstriction, total peripheral resistance increases. And this is going to lead to an increase in blood pressure. returning it back to normal. So what is the relationship between cardiac output and blood pressure? Remember, cardiac output is the amount of blood that is being pumped out by each ventricle per minute. More blood in your vessels means blood pressure will go up. Be sure that you understand how this reflex works. Let's look at some short-term neural regulations of the arterial blood pressure involving chemoreceptors. So this is the chemoreceptor reflex. It will work much the same way. The receptors are going to be located near the baroreceptors. They will be called the carotid bodies and the aortic bodies. Since these chemoreceptors are part of the peripheral nervous system, we're going to call them peripheral chemoreceptors. You also have another set of chemoreceptors located within the medulla, which is part of the central nervous system, so we'll call those central chemoreceptors. The peripheral chemoreceptors are monitoring the levels of oxygen, carbon dioxide, and the pH of the blood. The central chemoreceptors are monitoring pH related to carbon dioxide levels. So the stimuli will be a decrease in oxygen, an increase in carbon dioxide, or a decrease in pH. Recall, the central chemoreceptors will only pick up a change in pH, a drop in pH that is related to carbon dioxide levels. This is because carbon dioxide can go across the blood-brain barrier, but metabolic acids cannot. Therefore, metabolic acids will not influence the central chemoreceptors. These will be some new terms for you. Hypoxia is low levels of oxygen in the arteries. Hypercapnia is elevated carbon dioxide levels in the blood. And acidosis is decreased pH when it drops below 7.35. Remember, the normal range for your pH is between 7.35 and 7.45. The control center will be the same center, the cardiovascular center in the medulla. The effectors will be the same: the heart, including the SA and the AV nodes, and the myocardium, and the smooth muscles within your blood vessels. Remember, the SA and the AV nodes are innervated by both the sympathetic and parasympathetic branches of the autonomic nervous system, but the myocardium is innervated only by the sympathetic branch. The vascular smooth muscles are innervated by the sympathetic branch as well. This is the same illustration I showed you before when I pointed out the baroreceptors. You can see on the right the chemoreceptors, and notice how they're very close to where the baroreceptors are located. Let's review the chemoreceptor reflex. Chemoreceptors located in the periphery in the aortic and carotid bodies monitor blood oxygen, carbon dioxide, and pH levels. The central chemoreceptors in the medulla will monitor pH based on the carbon dioxide levels. When you have a decrease in oxygen or an increase in carbon dioxide or a decrease in pH, this will decrease the parasympathetic input to the heart, the SA and the AV nodes, and increase the sympathetic input to the SA and the AV nodes, the myocardium, as well as the smooth muscles in the blood vessels. This in turn will increase your heart rate, your stroke volume, and vasoconstriction. This in turn will increase venous return, allowing the blood to go back to the lungs much quicker so that you can have gas exchange, returning oxygen levels back to normal and/or carbon dioxide levels and pH. Let's look at short-term regulation of arterial blood pressure. This will involve hormones. The adrenal medulla, recall, releases epinephrine and norepinephrine in response to sympathetic input. These hormones are going to bring about the same actions as the neural transmitter norepinephrine. So they will bring about vasoconstriction. In addition, they will increase heart rate and contractility. Angiotensin II is a vasoconstrictor. Antidiuretic hormone is also a vasoconstrictor. For that reason, it is known as vasopressin. That is its second name. So all of these hormones listed so far are vasoconstrictors, which will increase blood pressure. The last, atrial natriuretic peptide, will do the opposite. This will bring about vasodilation. Long-term regulation of the arterial blood pressure is going to involve the kidneys. Renal refers to kidneys. Let's begin with the direct renal mechanism. If you have an increase in plasma volume or blood pressure, this is going to increase filtration. Filtration, if you recall from bulk flow, is the movement of fluid across a membrane from an area of high pressure to an area of low pressure. If your blood pressure is elevated, this will increase the filtration rate, decrease reabsorption, and therefore increase urine output, returning blood pressure back to normal. The opposite is true. A decrease in blood pressure will decrease filtration, increasing reabsorption, and decrease urine output. In addition, there is an indirect renal mechanism which involves the renin-angiotensin II aldosterone system, or RAS. We've covered this before, and we will continue to look at this throughout the semester. But recall, when blood pressure drops, renin is released by the kidneys. We've already looked at some actions of angiotensin II. We'll continue to look at those actions in the next slide. This flowchart is helpful when studying the renal mechanisms involved in regulating your blood pressure. On the left, you have the direct renal mechanisms. We've already talked about this in some detail. You may want to stop the video and study this chart. But I would like to go ahead and move on to the right side of the chart, looking at the indirect renal mechanisms, the renin-angiotensin aldosterone system, involved in regulating your blood pressure. So what we're going to look at here is a drop in blood pressure. Recall that a drop in blood pressure causes the kidneys to release renin. Renin, in response, will function as an enzyme to convert angiotensinogen into angiotensin I. Angiotensin I then is converted into angiotensin II by the enzyme called ACE, angiotensin converting enzyme. Next, you'll see all of the actions of angiotensin II. It goes to the adrenal cortex and causes the release of aldosterone, which in turn will go to the kidneys and increase sodium reabsorption. Recall that water will follow sodium. In addition, aldosterone also causes the release of ADH, which will increase water reabsorption at the kidneys. It will go to the hypothalamus, to the thirst center, and stimulate you to increase your intake of water. In addition, recall that it is a vasoconstrictor. All of these actions are going to increase your mean arterial blood pressure, returning the blood back to the heart. This is another flow chart illustrating factors that will determine blood pressure. I encourage you to stop the video and go through this flow chart. It puts it all together for you. I have one more thing I want to cover. Angiogenesis. Genesis means to make. Angial means blood vessels. This is making new blood vessels. When you have tissues that are consistently metabolically active, cells can release growth hormones that will stimulate the growth of new blood vessels. This photograph is of a heart that has been injected with these chemicals. You can see the increase in blood vessels. Finally, in conclusion, read about cardiovascular diseases and the effects of aging on your heart. I will hold you responsible for knowing this information. This concludes Chapter 19.